Okay, this is video 2 of the muscular dystrophy case, and now I'm going to start covering session questions that had a relevant physiological component. Just a quick review of what I thought you needed to take away and what the correct answers were. So this was a muscular dystrophy case, so obviously we're talking about a case where we have mutations in this dystrophin complex, okay? Dystrophin glycoprotein complex. And the first question was just basically describe the function of this complex. I'm not going to go through the layman's terms. I'll let the clinicians worry about how you break that to the parents. But physiologically, what this complex does is it connects actin in the skeletal muscle. For the record, this is non-sarcomeric actin. It's not the same actin that actually is involved in contraction, but nevertheless, this is part of the cytoskeleton, and it's all hooked up together, and it connects this actin to the membrane, and then from the membrane into the extracellular matrix, where it embeds in the matrix. So what happens is this muscle contracts in here. And because you have this connection through the dystrophin glycoprotein complex between the cytoskeleton inside and the extracellular matrix outside, you have the cytoskeleton literally dragging the matrix along as you contract. And so the cytoskeleton is bearing the force of the contraction. It's bearing, it's actually providing the force needed to drag the muscle along with the myofilaments that are contracting inside. So this is your connection. You have the myofilaments contracting here, and it's literally dragging the matrix and all the other muscle along with it, okay? And it's bearing the force of the contraction. And that's its normal function, okay? Its normal function is to provide this connection so that the inside of the cell is connected to the outside of the cell, and they basically contract together, all right? Now explain what happens when you have a mutation. Well, this connection is no longer there. So now the inside of your muscle contracts, but there's no connection through the membrane to the extracellular matrix. So what happens? The cell contracts, the membrane's being dragged along as the cell contracts, and because this connection is not there, the membrane is bearing the force that's needed to drag the extracellular matrix along. In other words, because there's no connection between the cytoskeleton and the extracellular matrix, now what's happening is the extracellular matrix is being dragged along by the membrane, which is being dragged along sort of by the actin and myosin contraction, and the membrane is bearing a lot of that force. Because there's no direct connection between these two, it has to act as an intermediate between them, and it can't stand that. It doesn't have the ability to bear that kind of force of contraction. So what happens is the membrane tears, and you get what are called microtears. And when you get microtears, calcium rushes into the cell dies. You get activation of proteases, and you get apoptosis in the cell, and it dies. And that's how muscular dystrophy works. That's how the disease progresses, okay? So 15 years after the initial diagnosis, Juan is admitted, and he requires intubation. And you give him succinylcholine prior to intubation, and this is not a good idea. The intern suggests it, and you say, no, don't do that. Because what happens is succinylcholine causes hyperkalemia. And so the question is, explain why you get the hyperkalemia and why it's very dangerous in a muscular dystrophy patient. A muscular dystrophy patient has upregulation of the nicotinic ACH receptors, so it has more than the usual number. And in fact, this is true of a variety of neural and muscular diseases. And why would this cause hyperkalemia? And the reason, and this, by the way, this happens in normal patients too. But if you're a normal patient with normal kidneys and you've got a normal level of potassium to start with, which you should, then you can handle the extra potassium that's released. It's like 0.5 millimolar or something like that, or up to 1 millimolar, but you can handle that. The problem with the muscular dystrophy patients is that because the ACH receptors are upregulated, that hyperkalemia is exaggerated and you're releasing more than the usual amount of potassium. And that's not good. So how does this work? The succinylcholine binds to the nicotinic ACH receptor, and it causes prolonged activation, prolonged openings of the channel, receptor channel. Now the way it works is, you activate the receptor and then it desensitizes after with prolonged activation. And so that's how you get your muscle relaxation, through the desensitization of the receptor. However, during that period when it's bound and the receptor is active, you have sodium coming in through the channel, and that's causing your depolarization in your motor end plate, which is its function, but you also have potassium going out of the channel at the same time. So the nicotinic ACH receptor is what's known as a nonspecific cation channel. And because you have this potassium efflux, you get an accumulation of potassium in the plasma because you have a lot of skeletal muscle in your body. It's 40% of your body weight, okay? So the potassium accumulates in the plasma, you get a hyperkalemia. Well, the more of these receptors you have, the worse the hyperkalemia. If you're a muscular dystrophy patient, then you've got a lot of them. And if you've got a lot of them, then you're going to get a severe hyperkalemia, and you run the risk of arrhythmias and all the bad things that come with hyperkalemia. Okay, so that's the major reason why you get the hyperkalemia. Another reason, and something that may contribute to this effect, if you depolarize the motor end plate and you get an end plate potential, and it's a prolonged end plate potential, and if you've ever seen a patient that gets succinylcholine, there's this initial excitatory period followed by the relaxation that you want. Well, if you get prolonged depolarization of that end plate, you're getting that excitatory period. That means you're firing repeated action potentials in the sarcolemma due to the fact that you've got this end plate potential that's got a nice high voltage. Well, repeated action potentials means sodium influx and then potassium efflux. And with that potassium efflux that comes with the repeated action potentials, you get accumulation of potassium as well on the extracellular side. And so that can contribute to this as well. This is probably the major factor, but this can contribute as well. It's something you should recognize. But you can get an accumulation of potassium just due to the fact that you're throwing action potentials, and during the repolarization phase, you have potassium exiting the cell through delayed rectifier channels. Okay? All right. So then we also had some questions on a malignant hyperthermia case. So you were given 8 possible reasons why the temperature might be rising in this patient, and why he or she might be having stiff skeletal muscle, repeated contractures, hypercontraction of the skeletal muscle. And one of the questions we asked you was, why do you think the patient's core temperature is rising? Well, what happens is whenever you hydrolyze ATP for energy, a certain amount of that energy goes toward doing whatever you want your protein, your ATPase, to do. If it's the SR calcium pump, it goes toward transporting calcium into the SR. About 20 to 30% of the energy goes into that. The other 80 or 70% is released as heat. So your body is not a very efficient machine. And so if you're hydrolyzing a lot of ATP, you're going to generate a lot of heat. And if you generate a lot of heat in skeletal muscle, which is a large percentage of your body weight, you could overheat, and that's what's happening here. Okay? We told you about succinylcholine, and we asked you, does the fact that this patient is on succinylcholine eliminate any of these 8 possibilities? Well, here's the bottom line. If you have desensitized your ACH receptors, your nicotinic ACH receptors on your postsynaptic membrane, anything upstream of that can't be causing the hypercontraction, the contraction of the skeletal muscle. Because without ACH receptors, you can release as much ACH as you want into the cleft, nothing's going to happen to the muscle cell. Okay, so we know it isn't a wild release of ACH because there are no receptors for it. They're desensitized. We know it's not the spinal neurons or the motor cortex, a seizure, because that would require, in order for the signal to be to go from the motor cortex to the skeletal muscle and cause a contraction, you would need nicotinic ACH receptors that are working, and because they're desensitized here, that can't be the case. So you can eliminate 1 through 4 from the list, okay? Just due to the fact that succinylcholine is what's causing this. You do an electromyogram on the muscle, and what does this tell you? Well, an electromyogram is like an ECG for your skeletal muscles or for your nerves. You have a cathode and an electrode, and what you do is you measure the potential difference between the two, just like you do with an ECG. And when an action potential propagates, let's say through the muscle cell, as it does in an ECG, you get a deflection as the action potential propagates through the heart. Well, as the action potential propagates through the skeletal muscle, you get a deflection on your EMG. So this guy, or I think it's a guy, maybe it's a gal, I can't remember. This patient has a flat line on the EMG, no electrical activity. So what do you eliminate? Well, we have number 5 here, which is a disorder of the skeletal muscle sarcolemma that could lead to spontaneous firing of action potentials. Well, if there were spontaneous firing of action potentials, you would have deflections on your EMG, and you don't. It's flat. So we know that 5 can't be the case. There's no electrical activity, so there are no action potentials. We're getting contraction that is action potential independent, okay? So we're left with 6, 7, and 8. And we ask you, okay, which of these is the most likely cause based upon what you know about the expenditure of metabolic energy that would take place if 6 or 7 or 8 were the case. So let's take a look at this. Here's our 6, 7, and 8. And let's start with number 7. The SR calcium pump stops working and prevents reuptake of calcium. Now we have 3 major eaters of ATP in your skeletal muscle. You have your sodium potassium ATPase, which is pretty much universal in all your cells, your myosin ATPase, and you have your SR calcium ATPase, okay? This, of course, is involved with contraction. This is involved with calcium reuptake into the SR. All of these eat a lot of ATP. So let's ask ourselves about the activity of each of these ATPases if 7 were the case. Well, the sodium potassium ATPase probably isn't going to be affected if this is the problem, okay? If the SR calcium pump stops working. So we can say that that's still active, all right? How about the myosin ATPase? Well, if we don't have an SR calcium pump and we're not taking calcium up into the SR, that means we have a high cytosolic calcium. And a high cytosolic calcium means we have lots of binding to troponin C, we have lots of muscular contraction going on, and lots of myosin ATPase activity. So this is probably very active in this case. So far so good. But if our SR calcium pump is stopped, that means our SR calcium ATPase is not active at all. So only 2 of our 3 ATPases are active in case number 7. So it's still a possibility, but maybe there's some, maybe not the best, given that, 1/3 of our 3 isn't active at all in this case. Let's look at possibility 8. This is malfunction at the level of the myofilaments. So let's say there's a problem with the troponin tropomyosin such that the tropomyosin is moved away from myosin binding sites on your actin, and your myosin can constantly interact with the actin with no rest at all. You're just constantly contracting. So would that affect the sodium potassium pump? Probably not. It's still active. Your myosin ATPase would certainly be very active because your tropomyosin is not in the way anymore. And so it's just going to keep, you're just going to keep contracting. as long as the myosin can bind to the actin, okay? The calcium is low here. The SR calcium pump is still intact. It can take calcium up into the SR, but we're not getting any release causing this contraction. It's a problem with the myofilament. The myofilaments are contracting on their own. You don't need calcium if it's a problem with troponin and tropomyosin, such that the calcium is independent. So the calcium is pretty low in this case. So your SR calcium pump is there, but it has a low calcium in the cytosol. So that means it's probably pumping at a pretty slow rate. Cytosolic calcium is your substrate for your pump. And when you have low calcium, the SR calcium pump's working at a very low rate. At high calcium, it's working at a high rate, if it's normal. Okay? But here, with the calcium being low, there having been no calcium release to cause this contraction, it's just contracting on its own. The SR calcium activity is there, but it's kind of a low activity. So this is better than 7, but still not great. So let's take a look at what's happening with a malfunction in EC coupling. So this would be a malfunction such that we're getting a bunch of inappropriate SR calcium release, or even worse, the ryanodine receptor is propped open and stuck open, so you're constantly releasing calcium. So let's ask ourselves, does that affect the sodium potassium ATPase? Probably not. It should still be active. It's in the sarcolemma and won't be affected by this. What about the myosin ATPase? Well, if we're constantly releasing calcium, or if the channel's stuck open, the calcium is going to be very high in the cytosol. Your troponin C is going to have pulled the tropomyosin away because it's bound to calcium, and you're going to have a very high rate of contraction, a high myosin ATPase rate. So far, so good. What about the SR calcium ATPase? Well, here's the deal. If our ryanodine receptor is stuck open, or if it's open a lot, in the case of 6A, we're getting a lot of release of calcium. Calcium's high here. Because the calcium's high, it's being taken back up into the SR through the SR calcium pump at a very high rate because the substrate's high. The cytosolic calcium's high, the pump's operating at a very high level. It's going crazy. So you're taking calcium, you're transporting it back into the SR. The problem is that if this channel's opening all the time, or if it's stuck open, that calcium's pumped into the SR and it comes right back out again. So you never accumulate that calcium back into the SR, and you have this vicious circle where you've short-circuited the uptake mechanism. So the SR calcium ATPase activity is going to be very high because you have high calcium in the cytosol and you can't bring that calcium down because it's just being re-released again. So of these 3, 6 is the most likely because it's the one, if we look at our 3 ATPases, it's the one that's going to be eating the most ATP, okay? And in fact, in most cases, it is in fact, in all cases, all known cases, it is in fact 6B, where the SR calcium release channel is stuck open. You have a mutation in the ryanodine receptor such that in the presence of certain volatile anesthetics or succinylcholine, in this case, you get the ryanodine receptor permanently stuck open, okay? All right. So we have another series of questions here. What is the source of the patient's acidosis? We have this muscle contracting like crazy. It's eating up ATP. Glycolysis can't keep up with it. Oxidative phosphorylation can't keep up with it. In part because the blood vessels in the area are probably being squeezed. Besides that, you're still eating it faster than you can make it. So you're generating a lot of lactic acid, and that's the source of the acidosis. How do you account for the hyperkalemia? Well, our ATP is dropping. So what do you think that does to the sodium potassium ATPase? It basically slows it down. Well, the sodium potassium ATPase usually pumps sodium out of the cell and it pumps potassium in. So without as much ATP, you're going to leave sodium in the cell. The intracellular sodium is going to rise. And in this case, what's much worse, the extracellular potassium will rise because your ATPase isn't pumping it back into the cell the way that it should. So you get a hyperkalemia. Why has the tendency toward hyperthermia decreased significantly? You're running out of ATP. less ATP hydrolysis, less heat generated by that hydrolysis. So the patient actually appears to be getting better when in fact he's actually getting worse, he or she. If the SR calcium release channel were stuck open, would there be differences in the way that the fiber types react? So ordinarily, when you just normally recruit muscle, you recruit slow oxidative fibers first, and then if you need more force, you will recruit the fast oxidative fibers, and finally the fast glycolytic fibers. However, here, we're just activating all of them at once because it's a problem with the ryanodine receptor. It's present in all those muscle cells, and so they're all hypercontracting all at once. So what happens? Well, your fast glycolytic are dependent upon glycolysis, and they're going to run out of ATP first because glycolysis can't keep up with this, okay? And you're going to be generating a lot of lactic acid because of that. They're going to be in the worst shape. Your fast oxidative fibers have a higher oxidative capacity, but they have only an intermediate resistance to fatigue. They are going to run out of ATP next, okay? And the slow oxidative are the most resistant to fatigue, but even their capacity is not unlimited. And if you are mostly dependent upon oxidative phosphorylation for generation of your ATP, that means you need that oxygen coming in, and if you're squeezing the blood vessels in the area, you're going to limit the amount of oxygen that you can get into the area, and that's going to make this worse as well, okay? You can't increase the blood flow through the release of metabolites if you're squeezing all the blood vessels, okay? And finally, can you account for the larger decrease in metabolic activity, that is the larger decrease in hyperthermia, than in muscular rigidity? So your muscles are still pretty rigid, despite the fact that the metabolic activity and the body temperature is falling. Why is that? Well, the reason is because as ATP falls, this whole thing slows down. Okay, and in particular, when it falls below a certain level, you don't have enough ATP to knock this myosin off of this actin molecule. You need ATP for these two things to separate like they are here. ATP binding takes place and the myosin separates from the actin at the same time. Without that ATP, you get stuck in what's called a Riger complex where the myosin is bound to actin and it can't unbind. And this causes stiffness in the muscle. So some of these fibers are probably contracting less as the ATP drops and this cycle slows down. But then the ATP falls below a certain level and all of a sudden your myosin is stuck on your actin and it can't be unstuck. And some of the muscle, some of the areas in the muscle are going to have Riger complexes that are going to maintain that stiffness. So you've still got a lot of stiffness in the muscle despite the fact that the ATP has dropped and the hyperthermia is getting better. So the Riger complexes are what's forming here. And of course, if you run out of ATP completely, you're dead, then you get what's called rigor mortis, and this is the reason why you get that, stiff muscles. Because there's no ATP, all the muscles are stiff and contracted, okay? All right. That's the end. Thank you for your attention. Good luck on the exam. Don't forget, I'm around. All you need to do is contact me. I'm glad to help.